All right, we are going to discuss section 5.6, which deals with indeterminate forms and, in particular, L'Hopital's rule. There are two main objectives. You can see them listed here. We are going to practice recognizing limits that produce what we call indeterminate forms. We have discussed indeterminate forms a little bit in the past, but we're going to discuss them in more detail here. And then, of course, be able to apply this new rule, L'Hopital's rule, which we also discussed in the past when we were doing a practice problem or two way back at the end of the first semester. I introduced this, but it wasn't formally introduced, and this is the section where we're going to discuss it in great detail. So we're going to be able to apply L'Hopital's rule in order to evaluate limits. All right, so here we go. First, a review of the indeterminate forms. Remember, this video is your resource, so if I go too fast or you don't quite understand something that was discussed, pause, rewind, back up, watch it again. All right, so here we go. Indeterminate forms. We have two primary indeterminate forms, and they are 0 over 0 and infinity over infinity. All right? We are looking for these two indeterminate forms in particular when dealing with or attempting to deal with L'Hopital's rule. Okay? So our formal process for solving limits, again, this goes all the way back to chapter 1 at the very beginning of the course. Our formal process is basically direct substitution. When we're asked to evaluate a limit as x approaches some particular value, we're going to take that value, in this case -1, and plug it directly into the function. And notice here, if you put -1 in here, you're going to end up with a positive 2 on top, minus 2, over -1 plus 1. So you will get, if you plug in -1, you will get the indeterminate form 0 over 0. So up until this section, our course of action for one of these limits, a limit that yields an indeterminate form, and if you've forgotten what that means, indeterminate means that the answer we've gotten from our math, this 0 over 0, is not our final work. That answer just reveals that there is more to determine. We cannot determine our result of this problem based on what has happened so far. It is indeterminate. So more has to be done. And our primary strategy up to this point has been use some algebra, just an algebraic method. Here we can take the numerator and just factor the 2 out. And then if you do that, you're left with, I'm sorry, not factor the 2 out. You're going to factor it entirely. You're going to factor it into 2 times x squared minus 1, and then the x squared minus 1 will factor into x minus 1, x plus 1, and then the x plus 1s will cancel on the top and the bottom, and you're left with only this. All right, so if you factor and you cancel appropriately, do what it says here, divide the numerator and the denominator by, I didn't mean to do that, divide the numerator and the denominator by x plus 1. All right, you take that factor out, you're left with just this statement. And then direct substitution will give us -4 as an answer. So through a little algebra, a little manipulation, we do get a real number value for this limit. All right, that was our strategy in the past. That's how we would solve this, and it's still how you should look to solve a problem like this. There's no need to go crazy, although you'll find that indeterminate forms are sometimes solved easier by using L'Hopital's rule, which we're about to discuss. The second equation here takes x and lets it approach infinity. And so if we're approaching infinity, our solution up until this point, our process has been to divide the numerator and the denominator by the highest power of x from the denominator, which of course in this case is x squared here. So we're going to divide 3x squared by x squared, divide 1 by x squared, divide 2x squared by x squared, and divide this 1 by x squared. So divide all 4 pieces by x squared, and you get this statement, 3 minus 1 over x squared, 2 plus 1 over x squared. Then if you apply the rule that said the limit as x approaches infinity of 1 over x to the r is always equal to 0, no matter what rational number r is, this limit will always be 0 if you're dividing some constant. It doesn't even have to be 1. It could be some constant a divided by x to a power r. And sometimes you see this r as an n for just any number. That means this term, 1 over x squared and 1 over x squared in the bottom, as x approaches infinity, you're dividing by an infinitely large number, this is going to go to 0. So if this is 0 and this is 0, you're left with just 3 over 2. That was our strategy for dealing with limits at infinity. All right, so we had two algebraic techniques to cancel out like factors, and then for infinite limits, we divide by the highest power of x in the denominator. All right, the next one is a little bit less obvious, I think, but if x approaches 0, then notice direct substitution. You put 0 in here, you get e to the 0, which is 1, over e to the 0 here, which is 1. So you've got 1 minus 1 over 1 minus 1. This is yielding an indeterminate form if you do direct substitution. All right? So the form here, I'll write it off to the side under the same section, is 0 over 0. So again, an algebraic method of factor and simplify will get you to a real answer here. So what have they done? They've recognized that e to the 2x is technically, this is not something that we see so clearly a lot of the times, but e to the x times e to the x is in fact e to the 2x, because you just, when multiplying like bases, you add exponents, so x plus x is 2x. So this is essentially kind of like this x squared minus 1 over here. E to the 2x minus 1 is going to factor in a similar way. E to the x plus 1 times e to the x minus 1. Then you can see that the factor of e to the x minus 1 over e to the x minus 1 will cancel. So that cancels with that. And you're left with just this e to the x plus 1 piece. So the limit as x approaches 0 of e to the x plus 1 is 1 plus 1 when you do direct substitution there. Put the 0 in for the x, and you get 1 plus 1 is 2. So this has a real number answer of 2. All right? Again, a little bit trickier, but it's certainly not out of the box. It's something that can be done. And that leaves us with this last example. How then would we solve just this little adjustment here? Noticed they've changed the denominator to just x. Numerator is the same. Factoring is not going to get us to simplify this any further. If you do direct substitution, you get 1 minus 1, which is, of course, 0 on the top. It's going to give you a 0 on the top. And if you divide by, as x approaches 0, you let x be 0, you're going to get 0 on the bottom. This is another indeterminate form of 0 over 0. So how do you solve it? If you can't use one of these algebraic techniques that we've just done, let's analyze it first with a table. So you can see here in this table, our function is e to the x, or e to the 2x minus 1 over x. And then we've got different x values that they're plugging in. So if they let x get closer and closer to 0, this is our question, you can see that they keep getting closer to 0 and closer to 0 from the left side. They let x be negative 1, let x be negative 0.1, let x be negative 0.01, let negative 0.001 to get closer and closer to 0. It appears that our answer is getting closer to 2. And the same thing is happening here on the right side. If you start with something as big as 1, which is not all that close to 0, but still closer than 5, and then you use 0.1, and then 0.01, and then 0.001, we're letting x approach 0 from the right, getting closer and closer. It looks like the answer is getting closer to 2. So just using a table, we would be able to estimate and say, we believe the answer here is 2. That's a table. You could look at it on a graph, and on a graph, it's very clear. If you put this into a calculator and you looked at it on the graph here, you would definitely see a curve that appears to have a limit of 2. Note, however, that it doesn't actually exist at 0, 2, I should say, because x cannot be 0, right? If you let x be 0, you have division by 0, so that number is not in the domain. So what happens is that there would be a hole in the graph at x equals 2. But that doesn't mean the limit can't be 2, because as long as both sides approach the same value, the limit exists. We know that fact. So we can confidently say that this is 2, but that is using 2 crude methods, a table and a graph. Algebra would be a more formal proof, would be a nicer way of showing that this is in fact 100% true. So that's where L'Hopital's rule comes in. Here is the rule in its glory, and we'll walk through it. Pause the video here, maybe take a moment to write it down. Okay, L'Hopital's rule says, suppose that we have 2 functions, f and g. Suppose both functions are differentiable. This is a key factor. Both functions should be differentiable. Obviously, the denominator cannot be 0. I say that obviously, but you'll see why when we actually look at the full rule. As long as both functions are differentiable and g prime of x is not equal to 0 on some open interval that contains the number a that we are approaching, all right, the number a, and a could be infinity. If the limit of f is 0 and the limit of g is 0, or the limit of f is infinity or negative infinity, all right, the limit approaches 0, both on the f, the f or the g, and go ahead and look down here. We're taking the limit of a quotient, right? F is the top, g is the bottom. So what we're saying is if the top is 0 and the bottom is 0, or the top is infinity, positive or negative, and the bottom is infinity, positive or negative. So if you get 0 over 0 or infinity over infinity, if you get one of these forms, then, and here's the rule in its glory, you can solve by taking the derivative of f prime, divided by the derivative of g prime, and calculate the same limit on the quotient of the derivatives. Again, as long as you get an indeterminate form, 0 over 0 or infinity over infinity, then the limit of f over g, if one of these forms is present, is equal to the limit of f prime over g prime. All right? So long as the limits exist. So 3 quick notes here, and the third one is really the best one, the most important one, but 3 quick notes. First, L'Hopital's rule says that the limit of a quotient of functions is equal to the limit of the quotient of their derivatives, provided that the given conditions are satisfied. Provided that the conditions are satisfied. You need to verify before you use L'Hopital's rule. Verify that you get 0 over 0 or infinity plus or minus over infinity. If you have not done that work, do not just blindly use L'Hopital's rule. All right? Note number 2, this rule also applies even if we're taking a one-sided limit or limits at infinity. So in other words, we don't have to just let x approach a. We can let x approach a from the right. We can let x approach a from the left. We can let it approach infinity. We can let it approach negative infinity. All right, and then finally, the third case, or third note here, talks about the special case, specific example, where f prime, where we get 0 over 0. The specific case for, special case for 0 over 0 here. if f of a and f of g both equal 0, and so long as the two derivatives are continuous, and of course the second derivative, or the derivative of g cannot equal 0, it's easy to see why this rule works. If we use the alternative form of the definition of derivative, this, by the way, is the alternative form of the definition of derivative right here. All right, you may remember that. We have the other form, which was the limit as h approaches 0 of f of x plus h minus f of a over h. This was our primary form for a derivative, but this, again, this was our primary, the way we memorized the definition of a derivative. This is f prime of x. But we also have this form, all right? And I should actually, I'm sorry, I should say this is f prime of a, the derivative at a point. But we also have this form. This is also the derivative at a point. Either one is fine, as long as we have a difference quotient. This is just a different way to represent the difference quotient. I'm not going to go into all the detail about why that's true. You should remember it. If not, just take my word for it. This is an alternative form. So what we're saying is, if we take the right side of this L'Hopital's rule, what I've boxed here, the limit as x approaches a of f prime over g prime, right? That should be equal to, according to our definitions for a limit, that should be equal to the limit. I can put this limit notation on the top and the bottom. It should be equal to the limit of the top, limit of this, divided by the limit of the bottom here. All right? So, if I rewrite using the formula for the definition of a derivative, the limit of f, you know what? I feel like there's a mistake here. I feel like this should not say, sorry to fumble this here for a second, but I feel like this should not have this prime on there, to be honest with you. I'm not sure why it has that. I'm getting caught up in this for a second. But anyway, let's just say that we wanted to take the limit of f prime over g prime, then it would be, sorry, the limit of f prime over g prime, then it would be literally the limit of this right here is f prime, and this right here is g prime. All right? So, what they do is they literally pull that limit off to the side, pull out the limit notation, and notice the algebra that's left, f of x minus f of a over x minus a, g of x minus g of a over x minus a. So if that's the case, then these x minus a's will cancel off, and we're just left with f of x minus f of a over g of x minus g of a. We already said at the beginning here that f of a was 0 and g of a was 0, so that leaves us with just the limit as x approaches a of f of x minus g of x. No, this was right from the beginning, now that I look at it. This was supposed to be here. This was supposed to be the limit of f prime over g prime. Limit of f prime over g prime would be equal to f prime of a over g prime of a. All right, and so what we're saying then is they are the same. This is an algebraic proof for the case where f prime, or sorry, f of a and g of a both equal 0. All right? It looks a little bit cleaner on a graph, I think, even. So if I look at that same idea on a graph, it says figure 1 suggests visually why L'Hopital's rule might be true. The first graph shows two differentiable functions, f and g, and each function approaches 0 as x approaches a. And you can see that here. Here's the f at this point on the x-axis where x is a, f is 0, and then here's g, and g is also 0. They both seem to be at 0 on the x-axis, all right? If you were to zoom in close enough to those, if you were to zoom in way into F and G, you can see here as I zoom in, that's about as far as I can go, that they almost do start to look linear, but of course zoom in even further, then both those functions would be linear. That is what we call the linearization. The linearization is the derivative, right? That's the tangent line. So if you were to zoom in, you would get a line for F, and we'll say that that line is some line y equals m some slope times x minus a, and this slope, of course, would be the slope of the tangent line. That would be f prime of a. And then you could do the same thing for g. You get a new line. That would be, we'll say m2 would be g prime of a, right? And so technically you've linearized the curves, right, and represented them as a line. So then f, the limit of f over g would be equal to the f line over the g line, and notice that the x minus a's will just cancel, and you're left with the slope. Well, what are those slopes? M1, as I just said, is the slope of the first line, and M2 is the slope of the second line. The slope of the tangent line on F and the slope of the tangent line on G, that's what these lines represent, right? And so the limit of F over G is equal to the limit of the slope of F over the slope of G. All right, very, very elegant, I think, graphical proof here for why it works in this special case. Finally, before we get to the examples, one last note, and that is, I will repeat one more time, notice that when using L'Hopital's rule, we differentiate the numerator and the denominator separately. We are not using the quotient rule, right? Do not use the quotient rule here. That's an entirely different thing. All right, so be careful when you're doing L'Hopital's rule. All right, example 1. Indeterminate form is 0 over 0. This is the exact same problem that we just had. We looked at it on, up here, we looked at it on a table. It seemed to approach 2. We looked at it on a graph. It definitely approached 2. Now we've got L'Hopital's rule in our toolbox. Let's use it. We know that it gives 0 over 0 as an indeterminate form. So L'Hopital's rule, I usually put a little h over the arrow that I draw to show that that's what I've done in this step, is I've applied L'Hopital's rule. All right, direct substitution gave me 0 over 0, but L'Hopital's rule will rewrite this limit as the limit as x approaches 0 of the derivative of the top. The derivative of the top is e to the 2x times 2, right? And then minus 0, because the derivative of 1 is 0. So the derivative here is this. The derivative of 1 is 0. And of course, the derivative of x in the bottom is 1. And so this is the limit as x approaches 0 of 2e to the 2x. And direct substitution now gives me 2 times e to the 0, which is 2. It has been proven. We expected the answer to be 2, and sure enough, the answer was 2. All right. There's a little history note on the side. L'Hopital's rule was named after French mathematician. I don't even know how to say his first name, to be honest with you. Guillaume Francois Antoine de L'Hopital. We're just going to go with de L'Hopital. L'Hopital is credited with writing the first text on differential calculus in 1696, in which the rule publicly appeared. It was recently discovered that the rule was and its proof were actually written in a letter from John Bernoulli. There were two Bernoulli brothers, by the way. But John Bernoulli wrote it in a letter to L'Hopital. It was just that L'Hopital put it in a book first, so he got credit. And he said, I acknowledge that I owe very much to the bright minds of Bernoulli brothers, and have made free use of their discoveries. That was a quote by L'Hopital. So in the solution to example 1, go back and note that you actually do not know the first limit is equal to the second limit until you have shown that the second limit exists. In other words, if the second limit had not existed, if we did not get a limit that existed here, then we would not have been permissible to use L'Hopital's rule. Just a little side note. And we got to make sure that there's an answer here. We can't get a DNE for this. All right. That's going to rarely happen, so I'm not going to worry about it. All right, moving on. Next example here. So if we have the limit as x approaches infinity now, it's very clear to see that the bottom will approach infinity if we just use direct substitution, right? But many of you may have forgotten what ln of x looks like. Just as a refresher here, ln of x when graphed looks like this, right? This is y equals ln of x. So as x gets bigger and bigger and bigger, the function grows. It's going to the right fashion, it's going up, but it is going up. So it's going to approach infinity also. And obviously, x approaches infinity, so there's no worry about the denominator here. It does give us infinity over infinity. Since we have verified that we have infinity over infinity, we can now use L'Hopital's rule. All right, so it will give us the limit as x approaches infinity of the derivative at the top. The derivative of ln of x is 1 over x, and the derivative of the bottom, derivative of x, is 1. And so, of course, we're dealing with the limit as x approaches infinity of 1 over x, and as x approaches infinity here, 1 over infinity is 0. All right? So our answer is 0. Cannot seem to get these squares to show up right sometimes. There we go. A little note here says, use a graphing utility. If you were to use a graphing utility, y equals ln of x and y equals x in the same viewing window, and consider which one grows faster as x approaches 0, you'd see some interesting stuff here. I'm not going to do that, but it's a nice little test. You could plug that into a calculator and play with it and see how they're related and how that observation takes place. All right, let's move on. Apply L'Hopital's rule more than once is what it says. So it's given us a hint on how we're going to have to do this problem. And it's a helpful hint. So just as a check, if we use direct substitution and let x approach negative infinity squared, of course, is positive infinity on the top. On the bottom, e to the infinity is what's going to happen, right? Because we're putting negative infinity into a negative x already. So it's e to the infinity, which obviously is going to get infinitely large. So that's going to be infinity, right? So we have infinity over infinity. We have verified. Let's move on. If we apply L'Hopital's rule, the limit as x approaches negative infinity, we get 2x on the top over negative e to the negative x on the bottom. All right? If we do direct substitution again, we're still going to get, in this case, we're going to get negative infinity, and in the bottom, negative infinity. So we still have an infinity over infinity scenario, and it's not helping us. It's not getting us any closer to an actual answer. So we're going to do it again. You can use L'Hopital's rule in succession as many times as you have to, so long as you keep getting an indeterminate form. Not a DNE. Remember, that was a note that we had here. Not a DNE. Not a does not exist, but an indeterminate form, 0 over 0 or infinity over infinity. So if I use it again, the limit as x approaches negative infinity, the derivative of now 2x is 2, and the derivative of negative e to the negative x gets me back to positive e to the negative x. And so now, direct substitution is going to leave me with 2 over infinity, and 2 divided by infinity, 2 divided in infinitely smaller pieces, of course, is just 0. Each piece will be so small that they are basically 0. So the answer is 0. All right? So example where it was used more than once. Let's keep going. Example 4. If I let x approach 0, tangent of 0 is 0. And of course, we're subtracting x equals 0, and then it's 0 cubed. So we do get a 0 over 0 if we do direct substitution. All right. If I use L'Hopital's rule, this one's pretty creative. I'm going to end up needing a little bit more space here. So let me try to squeeze in a little bit tighter and draw smaller. All right, the limit as x approaches 0. The derivative of tangent is secant squared. And of course, the derivative of x is 1. And on the bottom, I get 3x squared. All right? Direct substitution. Secant of 0 is 1. So I'm going to get 1 minus 1 is 0. And of course, 0 on the bottom. So I still have an indeterminate form. So I'll do it again. L'Hopital's rule applied again. This is where it gets a little bit trickier. Derivative of secant is secant x tangent x, but we're not dealing with secant. We're dealing with secant squared. So this is a chain rule problem. This is going to be 2 times secant to the 1 less power, so secant, times the derivative of secant, which is secant x, tangent x. All right? And of course, the derivative of 1 is 0, so I don't need that anymore. And on the bottom, I'm multiplying by 2 and decreasing the power, so I get 6x. All right? And now I could simplify that just a hair. Gives me 2 secant squared x tangent x. And it is all over 6x. And now this is a spot where most students will go, okay, well, if I plug in 0, I get 1 for this, and I get 0 for tangent of 0 is 0, over 0. I have it again, so let me do L'Hopital's rule again on this. Yeah, you can do that if you want, but that's a little tricky, because now you've got product rule and a chain rule in the same derivative. Instead, let's use one of those properties of limits that makes limits so darn fun, right? We have properties of limits that allow us to break limits apart. Not many other types of problems work in this way, but limits allow us to be flexible with how we play with them. I could split this whole thing apart and call it, in fact, first I'll say I can pull off the 1/6. I do not like that highlighting. That's a little bit much. Let's go with this. I can pull off the 2 over 6 and call it 1/3. I said 1/6. I should have said 1/3. I can pull that way out in front. That's just a constant. A constant inside of a limit is the same as a limit, or the same as putting the constant in the front of the limit. So that's 1/3 out in front. And then I can actually split this into the limit as x approaches 0 of secant squared times the limit as x approaches 0 of tan x over x. That's totally legal. You can distribute limit notation into each piece and break it apart into multiple products, or a product of multiple pieces. So I got this 1/3 hanging out in front. Again, that was from the 2/6. And then I've got the limit of secant squared and the limit of tan x over x. Well, the limit of secant squared is easy. We know that value. That's 1. And that's where I might be able to do, or I might say, okay, well, let me play around with that and let me do L'Hopital's rule on that again, right? If I apply, I should have left a lot more space for this problem, clearly. If I apply L'Hopital's rule here, then this is the limit as x approaches 0 of derivative of tangent is secant squared, and the derivative of x is 1. So it gives me another 1, right? So what do I really have? I'm looking at 1/3 times this limit as x approaches 0 of secant squared is 1 times this limit of tan x over x as x approaches 0 is another 1. And my final answer is 1/3. All right, you might have guessed that if you saw that factor sitting out in front here earlier, but maybe not. So there you have it. A little bit trickier. We ended up using L'Hopital's rule in 3 separate places, 3 different places. But you could have, again, just used the chain rule and product rule to differentiate this, and then use, L'Hopital's rule, or split it up. This very tricky problem, to be honest with you. All right, last note here, and I'll end the video. is about just being careful. Make sure you have verified L'Hopital's rule. All right. So this example here is a one-sided limit. That's why I like this example, because we haven't done one yet. The limit as x approaches pi from the left of sine over 1 minus cosine. If you just blindly use L'Hopital's rule without plugging in pi, all right, one-sided limits, we still just plug in the a value. In this case, a is pi. If I plug in, or if I do L'Hopital's rule, the derivative of sine is cosine. So you'll see right here, this is where they're doing L'Hopital's rule. The derivative of sine is cosine over 1 minus cosine. The derivative of negative cosine would be positive sine, right? Equals negative infinity. So as x approaches pi, it equals negative infinity because cosine of pi is -1 and sine of pi is 0. And that's a problem, right? You're dividing by 0. That's not an indeterminate form. This, again, would give you, before you get to negative infinity, you would actually have -1 over 0. And that is a DNE, but if you analyze it on a graph, if you look at what this behavior of cosine over sine, it's tangent, right? Cotangent. The graph of cosine over sine is really the graph of cotan. And the graph of cotan looks like this, with an asymptote at pi. And as we approach pi from the left side, we are approaching negative infinity. The graph is going down forever, right? Again, this is y equals cotan, which is what cosine over sine is. It's cotan. All right. So just verifying, this is cotan x. It does approach negative infinity. So you'd be tempted, if you just use L'Hopital's rule blindly, you would be tempted to say, okay, my answer is negative infinity. And that would be wrong. First of all, notice this doesn't exist. This is a limit that doesn't exist. If you get negative infinity, that's false. All right? That is a no limit. It's limitless. Negative infinity is a limitless value. So that would be a red flag right away. But if you even got a value here, it still would be wrong. Why? Because we never checked to see that we had an indeterminate form from the beginning. If you let sine approach pi, you get 0, yes. But if you let cosine approach pi, you get -1, which is 1 minus -1 is 2 in the denominator. So sine of pi is 0, and cosine of pi is -1, you get 0 over -2. 0 divided by -2 is 0. The limit here is actually 0. Not negative infinity. So this is a perfect example of what could go wrong if you fail to verify, like we did in every problem, that you started out with an indeterminate form. Every example, the first thing I did was verify that I had an indeterminate form. All right, and if you do, then you are able to apply L'Hopital's rule. But if you don't, you cannot apply L'Hopital's rule. All right? Okay, that ends this video. Part 2 will be in the next video. Thank you.